Antonevich, and I'm a senior at the College of William & Mary. And over the past couple months, I've been working on a project focusing on pitch sequencing. This project originally started as a very small paper I wrote for a class last fall, and I was really interested in the paper and interested in the work, so I just kind of kept working on it throughout the semester, and I'm excited to share with you all today what I've been working on. So let's start by considering the factors that determine the outcome of a single pitch. So whether or not a pitch results in a ball, a strike, a swing strike, a ball in play, etc. We can really group these factors into two categories. We can think of the decisions that the batter, the pitcher, and the catcher make, and then the execution of these decisions. So when we think about the decisions a pitcher makes prior to throwing a pitch, he's thinking about a lot of things, but essentially he's thinking about what pitch type to throw and where to throw that pitch. Now, he makes these decisions, again, based on a lot of factors, but effectively he's thinking about the relative quality of his pitches, whether he's got a really sharp fastball, a fringe changeup, etc., the relative strengths and weaknesses of the batter he's facing, and then the previous pitches he's thrown in that plate appearance. So when we think about pitch sequencing, we can really think about pitch sequencing as how the previous pitches thrown in a plate appearance impact the expected outcomes on this pitcher's pitches, and then further inform the optimal decision for him to make in this plate appearance. So traditionally, pitch sequencing has been a really challenging area of baseball to study. It really can be challenging to properly assign credit or blame for the outcome of a single pitch. So say, for example, a batter swings and misses at a curveball low and away. Did he swing and miss because it was a really great curveball just in general? He traditionally struggles against curveballs low and away. He made a decision while the ball was on its flight to the plate that ended up being the wrong decision, or a product of pitch sequencing or some other factor like that. So because of this, previous research in the public domain has really focused on studying pitch sequencing in aggregate, looking at outcomes on successive pitches while varying one specific component of pitch sequencing. From this previous research, we know that pitchers that are able to effectively tunnel two successive pitches of different pitch types see an increase in their swing strike rate on that second pitch, really supporting a lot of what's been talked about at this conference this weekend about tunneling, and really supporting kind of the traditional beliefs about tunneling there. Additionally, previous research has supported kind of the traditional adages of pitch sequencing that are really accessible to really any type of fan. The idea that mixing pitch speeds as well as locations on successive pitches leads to an increase in swing strike rate or an increase in pitcher success in some way on that second pitch. So previous research has shown that doing so, to some extent, increases swing strike rate on the second pitch of a two-pitch pairing. So, as I said, prior research has really explored pitch sequencing along these specific dimensions. So varying pitch speed on two successive pitches, we're studying the variation in pitch speed on two successive pitches, and then seeing how that impacts swing strike rate on that second pitch. However, I was interested in trying to aggregate a lot of these effects into one model to understand not only how varying pitch speeds and pitch locations and tunneling impacts the outcomes on two successive pitches, but also how it bears itself out in these specific matchups. I think some previous research supports the idea that pitch sequencing effects are really batter and pitcher dependent, as Vince Gennaro showed in his presentation yesterday, that it might be the case for some pitchers that the previous pitch really doesn't have a lot of importance in determining the outcomes on the current pitch. And as well as Russell Carlton's research supports the idea that a batter's ability to handle changing speeds is kind of an intrinsic ability that some batters have and some batters don't. So my research goal for this project was to create a program that produces the optimized a sequence of 5 pitch type and location pairings that maximizes expected swing strike rate at each pitch in this sequence. Once this program was built, I plan to use this program for subsequent analyses to try to understand how these beliefs about sequencing and how these general sequencing concepts bear themselves out in these particular matchups. So when I talk about a 5 pitch type location pairing sequence, this is what I'm talking about here. So here we have the pitch type for each pitch number, as well as the corresponding MLB game day zone that the program recommends throwing this pitch in. So for example, for this hypothetical matchup, the program first suggests throwing a 4-seam fastball in zone 6, which I'll touch on in just one second, but is the outside part of the plate. Then given that the program selected throwing a 4-seam fastball in this location, the program then suggests throwing a slider in zone 8. So the program continues to work from there, producing the optimal pitch type and location pairing that maximizes expected swing strike rate for each iteration of this sequence. So in order to produce a program or create a program that makes decisions based on expected swing strike rate, I first needed to figure out a way how to model expected swing strike rate. So to do this, I created my model based on the characteristics of the pitch in question, or the current pitch, the pitch whose expected string strike rate we're trying to estimate, as well as the prior pitch. So I passed variables to the model, including the horizontal and vertical movement of the pitch, the velocity, as well as the game day zone associated with this pitch. As many of us are probably familiar with the game day zone, game day zones are with 2018 StatCast data, simply assigns the pitch to one of these 13 discrete zones based on where it crosses the plate. So again, I pass these variables to the model for not only the particular pitch in question, but also the prior pitch as well, to really try to capture how the previous pitch and the quality of that pitch impacts the expected swing strike rate on this pitch in question. In addition to these StatCast metrics, I wanted to include some sort of tunneling metric based on the previous research that supports the idea that pitchers that are able to tunnel pitches effectively do see an increase in their performance on successive pitches. So to do this, I included the pre-tunnel maximum distance from Baseball Prospectus from the tunneling metrics that they produce there, which is just a measure of how far apart two consecutive pitches are at the decision point. So on its flight to the plate, how far are these two pitches apart at the decision point in which the batter needs to decide whether or not he's going to swing at the pitch. So to touch on some of the technical details of this, I know it's not perhaps the most engaging part of the presentation, so I'll just kind of touch on these quickly. So given these variables and given the structure of the model I wanted to build, I had to figure out a way how to figure out the most optimal modeling technique to create these estimates of expected swing strike rate. So after some quick preliminary analyses, I was able to quickly disregard some approaches and really settled on either using support vector machines or random forests to create my estimates of the likelihood of a swinging strike on a particular pitch. So to test these modeling approaches, I made many out-of-sample predictions after training models on specific subsets of matchup data, and then judged their performance on aggregate. So I judged model performance based on rock curves, not to get too into the weeds on rock curves as a whole, but they effectively show us how well a model is able to classify two different types of data in a set of data. So effectively, the rock curves show us how well the model is able to classify a pitch as resulting in a swinging strike or not resulting in a swinging strike. So the way to read these plots here is that we want a rock curve that is as far to the top left corner of the plot as possible, as that shows represents a model that is able to perfectly identify whether or not a pitch results in a swinging strike or doesn't result in a swinging strike. So here, it's very clear that the random forest is a superior modeling technique for this given problem. And additionally, some of the modeling techniques and kind of the model characteristics of the random forest kind of support this performance. Random forests are really good at capturing the interaction between variables in producing and estimating the likelihood of a dependent variable, and are able to capture kind of this complex relationship that exists between all of these pitch characteristics and locations. So it's able to say, for example, it's able to capture the impact of not only throwing a four-seam fastball on the pitch prior, but also throwing a four-seam fastball of this quality in this location in determining the outcome on this current pitch. So given this performance, I felt comfortable using the random forest to create my estimates of swinging strike rate throughout the running of the program. So to give a quick overview on this program that I continue to mention, the program is currently just stored on my computer. I wrote it in R, but I would like to plan on making it a little more usable kind of going forward. But to touch on kind of how it runs generally, first the program takes the batter ID and pitcher ID for this particular matchup that we're interested in investigating. So for the matchup that we're interested in generating this 5 pitch type location sequence for. So once these IDs are passed, the program then finds similar batters and similar pitchers to these players that were input to the model. So it finds similarity based on using Gower's distance, which is just a very simple measure of similarity between two observations. And I calculate similarity for pitchers based on their pitch type distribution, so what types of pitches they generally throw to hitters, as well as their average fastball velocity. I included average fastball velocity just because a pitcher a pitcher with a 99-mile-an-hour fastball is going to probably sequence and pitch to hitters a lot differently than a pitcher with just an 89-mile-an-hour fastball. For batters, I calculated similarity between batters based on their batted ball profile against pitchers of both handednesses. So the frequency of ground balls and line drives and fly balls that they put into play, as well as their average exit velocity and launch angle. Just again, because a pitcher is going to sequence to a hitter with a very high average exit velocity, like Mike Trout, like Giancarlo Stanton, differently than a hitter with a very low average exit velocity. So I wanted to really capture these impacts and calculating similarity between similars and pitchers, or between pitchers and hitters. So once I had these lists of similar pitchers and similar hitters, I then subsetted my main set of 2018 StatCast data to include only pitches thrown from either the pitch in question or the similar pitcher to the similar batters or the batter input into the model. So in doing this, I really sacrificed a large part of my sample as I shrunk my set of data significantly down from the 2018 season to just this group of pitchers and hitters. But in doing so, I was able to capture some of the matchup-specific nuances to this problem. So able to capture kind of some of the intrinsic factors about these pitchers and hitters, rather than trying to pass variables for the likelihood for a batter to swing at a ball low in the strike zone, the likelihood for a batter to swing high in the strike zone. These factors are kind of baked into this set of data. So from here, I then filter this subset of data again to include only pitches thrown in the first pitch of each plate appearance, and then I fit a random forest estimating the likelihood of a swinging strike based on the movement and velocity as well as the location of this pitch. So I'll call this the first pitch model. And it allows me to estimate the likelihood of a swinging strike on a particular pitch just without any sequencing impacts and just looking at these first pitches. Then going back to this original subset of data, I then fit a random forest on the components of each pitch and the components of each pitch preceding it based on the specifications previously discussed. So this allows me to estimate the likelihood of a swinging strike on a pitch in question, as well as based on the components of the pitch in question, as well as the prior pitch as well. So we'll call this the next pitch model. So it's important to note that, one more thing before I jump to this next slide, that every time the program is run and every time a sequence is generated, there's two new random forests created each time. So there's not one overarching model that I'm passing to this program repeatedly. I'm generating a random forest each time on this particularly filtered subset of data to really try to capture the effects or capture the nuances of this matchup for these batters and for these pitchers. So once I have these random forests created, the process for actually generating the 5 pitch type location sequence is relatively simple. So first, the program calculates the average movement and velocity for all pitch types for this given pitcher. So say I'm creating an optimized sequence for Chris Archer. The program will calculate the average movement and velocity of all of Chris Archer's pitch types. So his fastball, his slider, his changeup, curveball, what have you. So then, using each of these pitch types and their average movement and velocities, I calculate the expected swing strike rate for all pitch type and location pairings using this first pitch model. So what is the expected swing strike rate if Chris Archer throws a fastball in the first pitch in each of these 13 game day zones, or a slider in the first pitch in each of these game day zones? To get an understanding of the likelihood of a swinging strike based on all the possible combinations and all the possible decisions that Chris Archer could make. So then from there, I simply select the pitch type and location that maximizes expected swing strike rate for this first pitch. And we'll call that pitch 1. Given the pitch type and location that was selected for pitch 1, I pass that to the next pitch model and calculate the expected swing strike rate for the second pitch of this sequence. So given the pitch type and location that was selected in pitch 1, and given the characteristics of this pitch, what is the best option for Chris Archer to throw for this next pitch? So really trying to capture these sequencing impacts and understanding how they bear themselves out in this particular matchup. So again, I calculate all the expected swing strike rate for all pitch type and location pairings, and then simply again select the pitch type and location pairing that maximizes expected swing strike rate from this set of data. So then we call that pitch 2. So the program continues to run in this manner, estimating the likelihood of a swinging strike based on all possible combinations and all possible decisions that the pitcher could make based on the components, again, of the pitch in question as well as the prior pitch as well. So in doing so and in generating my optimized sequences in this manner, I'm able to capture kind of all of these factors that impact the decision that a pitcher makes. I'm capturing the average performance of his pitches by using the average movement and velocity of each of his pitches, as well as the relative strengths and weaknesses of the batter using this filtered subset of data of similar pitchers and similar hitters. And then additionally, the impact of sequencing by using this next pitch model. So a couple kind of overview notes about this program that'll be kind of relevant to the analyses that in the examples I give using the program. So the bagging inherent to random forest and the way random forests are generated results in a little bit of variation in between runs. So say, for example, I generate a 5-pitch optimized sequence for Chris Archer pitching to Mike Trout. And so I generate it once, and then I generate it again. There might be a little bit of variation in between these two sequences, just because of kind of the random nature of the random forest and the way it combines many decision trees in producing the probability of this event. There'll be a little bit of variation. But as I'll touch on in 1 second, we can use that to our advantage in getting an understanding of range of potential outcomes or potential sequences for the pitcher to use in this case. Additionally, there's a potential for one pitch type to really dominate the model output. So say I'm a reliever with a 99-mile-an-hour fastball and really only fringe off-speed pitches. The program could suggest that I simply throw my four-seam fastball and for all pitches in this pitch sequence for 5 consecutive times, just because my other stuff really isn't good enough to generate swing strikes with any sort of regularity. So, while this may be applicable in some sense, it's probably not applicable for a pitcher to do this kind of long-term and in a large set of plate appearances, just because you're not going to throw, only four-seam fastballs to this large group of hitters and instead probably want to mix in some sort of off-speed pitch regardless of how we feel the quality of the pitch is. So this could be controlled for some sort of selection logic, forcing the program to select an alternative pitch type and location pairing if a certain pairing has been selected some number of times already, but for the time being, I just left it as is. Additionally, the model output is based on real sequences and subsequent events, because it's based on how pitchers have previously sequenced and how the batter has responded based on the sequences and pitches that the pitcher threw. So this will lead to realistic results and kind of jive with what we traditionally believe about pitch sequencing, but it's also unlikely to propose anything truly dramatic. The program isn't going to suggest throwing change-ups high in the strike zone 5 consecutive times, just because not only is it infeasible and likely not an effective approach, but it's also something that pitchers generally don't do right now, so it's not going to show up in this data, and thus the model is not going to be able to produce sequences based on it. So overall, using an approach like this allows me to kind of embrace the complexity of the problem using these black box algorithms and really able to capture kind of the nuanced relationship between these pitch characteristics and the likelihood of generating a swinging strike. And as I'll touch on in a second, we can then work backwards to understand why the model makes certain decisions and really try to understand how these pieces of pitch sequencing and kind of how these traditional adages bear themselves out in this particular matchup. So I've touched on this a little bit already, but say we're interested in generating a 5-pitch sequence to try to understand how Chris Archer should best pitch to Mike Trout. So to do this, I generated 50 of these optimized sequences. So generated 50 of these 5 pitch type location pairing sequences and analyzed the aggregate results. So just to take a quick look at the output of the aggregated results and the output of the program, just from the surface level, not really looking at sequencing too much, just to kind of confirm that the model output makes sense and kind of falls in line with what we might, traditionally believe. We see here, looking at the pitch type distributions for each pitch number in these optimized sequences, we see that the program suggests throwing a slider in the first pitch of the sequence roughly 75% of the time, suggesting that pitching backwards to Mike Trout and starting Mike Trout off with a slider might be an effective approach for Chris Archer to take. From there, the program recommends primarily switching to fastballs after that, as we see fastballs dominate the chart here for pitches 2 and 3, and then switching it up toward the end of the sequence, throwing a combination of fastballs and sliders. Then, additionally, looking at the locations, we see that the program recommends throwing fastballs up and away, primarily to Mike Trout, and then sliders down, or sorry, up and away, and then down and away for sliders. And this again kind of follows the traditional beliefs about pitching and kind of where these pitches might have their performance maximized and are effective places to throw these pitches. So in addition to these surface level analyses, we can also look at the sequencing impacts in particular. So here's a table showing the frequency of different two pitch type location combinations in these aggregated results. So for example, there were 37 instances in these aggregated results of the program suggesting to first throw a slider down and away to Mike Trout, and then to have Archer throw a fastball up and away. So really we see that for the most common most common two pitch type location pairings, we see that the program recommends in some fashion throwing a breaking ball low in the zone or out of the zone, and then following it up with a four-seam fastball up and away, suggesting that for Chris Archer, both changing pitch speeds and locations is the most effective way for him to get swinging strikes against Mike Trout when looking at these two pitch sequences. And then additionally, we have 30 instances of the program recommending throwing successive four-seam fastballs down and in, and then the program recommending having 29 instances of recommending throwing a four-seam fastball up and away, and then a four-seam fastball down and in. So looking at these results, we can get an understanding of how these kind of traditional beliefs about pitch sequencing bear themselves out in this particular matchup of Chris Archer throwing to Mike Trout. So we don't see any instances of the program recommending throwing two pitches of different pitch types in the same location, suggesting that changing speeds only for Chris Archer isn't nearly as effective as both changing pitch speeds and pitch locations, or just changing locations, as we see in the bottom right corner here. So this gives us an understanding of kind of how Chris Archer can take these kind of adages about changing speeds and changing locations and use them in practice for this particular matchup. So additionally, we have the five pitch sequence that was most common in all of these aggregated sequences. So this is the whole sequence that dominated the model output or dominated the program output of all of these aggregated sequences. So here, we see a combination of mixing speeds, mixing locations, and giving kind of a roadmap of how Chris Archer might be able to achieve success in doing so. It's important to note that this doesn't suggest this is the only avenue for Chris Archer to pitch to Mike Trout, and there's a lot of other context-based factors that need to be considered if there's actually going to be implemented or something. We would need to work under the assumption that Chris Archer feels both of his pitches are at 100% for that given day. He has full confidence in throwing them. Then we also need to consider kind of how many times he's faced Mike Trout in the game already, and just a bunch of context-based factors that need to be considered in making this decision. So I see this more of as just kind of one potential data point for game planning for specific matchups, or considering matchups kind of in a hypothetical sense. So just kind of some main takeaways from this matchup-specific analyses. So we can generate a large number of optimized sequences for one particular matchup and analyze these results on aggregate. So these results suggest that throwing a low slider and then a high fastball from Chris Archer to Mike Trout has a high likelihood of success, where again, success is defined as generating a swinging strike. As we saw in the most common two pitch type location pairings, we saw the program really suggested throwing low sliders and then high fastballs as a method for generating swinging strikes in this particular matchup, and really stood out above the rest in terms of optimal ways to sequence these pitches. Additionally, Archer should consider throwing a first pitch slider, as we saw that in 75% of these optimized sequences, the program recommended throwing a first pitch slider to Mike Trout. Additionally, changing location seems to have a greater sequencing impact for Archer against Trout than changing just speeds. Again, we didn't see any examples of the program recommending throwing throwing the same pitch type on successive pitches or different pitch types on successive pitches in the same location. So the program never suggested to throw a slider in zone 8 and then a fastball in zone 8. The program recommended varying pitch speeds as well as pitch locations. Additionally, Archer should probably avoid throwing a changeup, as the program never selected a changeup as the optimal pitch type to throw to Trout, and this should be held at least in the first plate appearance. And this kind of makes sense intuitively. Trout being arguably the best hitter in the game, Chris Archer is going to stick to his best pitches and stick to what he knows works and knows has success. So in addition to these matchup-specific analyses, we can also generate some large number of optimized sequences for all pitchers of a given population against one specific batter. So for this example, I generated 4 optimized sequences for all right-handed pitchers in the MLB who threw at least 50 innings pitched in last season. And I generated all these sequences against Jose Altuve. This will give us a more general understanding of how to pitch to a specific hitter across a variety of pitch types and a variety of pitch qualities as well. So we can conduct the same type of analyses that we did in the Mike Trout, Chris Archer example, looking at the frequency of different pitch types at certain pitch numbers, looking at trends and tendencies in terms of location pairings and pitch types pairings. But in the interest of time, I'll just focus on one particular dimension of these analyses. So here we have another table showing the most frequent pitch type location pairings from these aggregated sequences. So I ended up with roughly something like 650 5-pitch sequences, and I analyzed these results in aggregate. So, for example, this table shows us that the program suggested throwing a curveball in zone 9, and then after that pitch, another curveball in zone 9 386 times. And so this definitely seems like a lot, and it is a lot, but it's also important to remember that of these 650 5-pitch sequences, there are something like 2,500, 2,600 possible 2-pitch type location pairings. So it's a lot, but it's not like the program is only recommending pitching in this manner. Really, we see that throwing breaking balls low and away to Jose Altuve dominates this program output in some fashion. We have curveballs, knuckle curves, sliders, all in these low and away strike zone, all in these low and away zones relative to the strike zone. So this is likely a product of availability. If a pitcher for a particular sequence doesn't have a great pitch to challenge Jose Altuve with, and really considering Jose Altuve, again, is one of the better hitters in baseball, it's not out of this world to think that a pitcher wouldn't have a great pitch to challenge Altuve with. The program is likely going to suggest just simply throwing breaking balls low and away to Altuve, just as this kind of pitch type location pairing has a relatively high propensity to generate a swinging strike in general, and is also a safe play for the batter, or safe play for the pitcher. The program isn't going to recommend throwing fastballs inside if the pitcher only has a fringe fastball to Jose Altuve, considered a very dangerous hitter. But I was interested in trying to determine what proportion of the program's recommendation to pitch in this way is a product of availability, or if there were some other characteristics about these curveballs and about these breaking balls that made them particularly useful to throw in succession in these particular zones. So I was said to look at this particular set of curveballs. So these 500 curveballs thrown in zone 9 or zone 14 successively. So to do this, I simply grouped curveballs into one of two groups. So I had my group of consecutive curveballs, or curveballs thrown by pitchers whom the program recommended throwing curveballs in succession in this manner. And then I had my group of non-consecutive curveballs, so curveballs thrown by pitchers whom the program did not recommend throwing their pitches in this manner. Then I simply calculated some basic summary statistics about these two groups and looked to see if there were any meaningful differences in pitch movements and in pitch characteristics between these two types of pitches. And as we can see here, looking at both means and density plots of some of the more interesting metrics, we see that there really isn't too much of a difference between the group of consecutive curveballs and non-consecutive curveballs. The consecutive curveballs had a little bit more vertical movement and perhaps a little bit of less velocity difference, where velocity difference is defined as the difference in pitch velocity between a pitcher's fastball and the pitcher's curveball. But really, the distributions and means look pretty similar. Perhaps a little bit of skew for the group of non-consecutive curveballs in terms of velocity difference, but for the most part, they look very, very similar, suggesting that the program's recommendation to throw pitch types in this manner, to throw curveballs in succession to Jose Altuve in these low and outside zones, is just a product of availability. Additionally, I was interested in looking at this, completing this same type of analyses for these fastballs recommended to throw to Jose Altuve down and in succession, so in zone 7. So again, I simply grouped fastballs based on called consecutive fastballs or non-consecutive fastballs. My group of consecutive fastballs are fastballs thrown by pitchers which the program recommended throwing their fastball down and in succession to Altuve, and then my group of non-consecutive fastballs, so just the inverse of that. So again, I calculated these summary statistics in between these two groups, and here we see differences that are a little more pronounced. We see that the group of consecutive fastballs had slightly more vertical movement while also having less pitch velocity than the non-consecutive fastballs. I found this to be particularly interesting just because it's a kind of an atypical fastball in terms of what we think about when we think about kind of how vertical movement and velocity tend to vary. It also suggests that perhaps there's a certain pitch type or a certain type of fastball that can be effectively located to Jose Altuve in this manner. However, these differences are slight, they're not statistically significant, and this could just be a product of a small sample size, but it does suggest that perhaps this is an area that warrants future research. So overall, I feel like I'm really just kind of scratching the surface in the types of batter-specific and matchup-specific analyses that I can complete with this program to understand how certain sequencing components really bear themselves out in these matchups. Additionally, I'd be interested in trying to take this a little bit further and make it a little more generalizable to try to understand, are there specific types of hitters, for example, that struggle against certain types of sequences? So say, for example, I find a group of hitters whom the program recommends pitchers varying pitch speeds more than pitch locations. Can I map this particular characteristic to something in their surface level stats as well to make these hitters a little more identifiable and try to understand how a hitter's surface level performance impacts the optimal sequencing decisions for a pitcher to make when pitching against them? Additionally, I'd be interested in optimizing to different targets. I'd be interested in looking at soft contact and ground balls or some combination of targets. I originally chose swinging strikes just based on the previous literature as well as kind of the stickiness year to year of a pitcher's swinging strike rate, suggesting it's something they have some sort of control over. But I'm interested in kind of furthering this approach and looking at a variety of targets. Additionally, I'd be interested in trying to control for pitches dominating the model the program output to try to understand when the program recommends throwing, say for example, 5 consecutive four-seam fastballs to a particular hitter. Is this a product of availability, or is this a product of the pitcher not being impacted by sequencing as much as others? As Vince Gennaro showed in his presentation yesterday, perhaps there are some pitchers specifically whose outcomes on a particular pitch are not really determined by the prior pitch and really just determined by this particular pitch in question. So overall, we can effectively model the likelihood of a swinging strike on a particular pitch based on the characteristics of this pitch in question as well as the pitch prior. And give us an understanding, and then this modeling technique can be put into this program to give us an understanding of how particular sequencing components and sequencing aspects really bear themselves out in this particular matchup. So to try to understand, for this particular pitcher pitching to this particular hitter, how can this pitcher best sequence his pitches, best mix speeds, best mix locations, and try to understand, given the pitcher's overall performance, the batter's relative strength and weaknesses, and the sequencing impacts, what's the best plan of approach for this particular hitter. So that's all the time I have this morning. I thank you very much for your time. I'd like to thank SABR for giving me the opportunity to speak and share my research this morning, and for the MLB for making all of this great data publicly available. I'll be sticking around for a bit if there are any questions. Thank you again.